centuries, man has tried with his inadequate tools to peer into the future and predict the weather. Such predictions are often sketchy and inconclusive, as it has been impossible to gather information from many vast areas of the Earth. The meteorologist has long dreamed of looking from the outside in, rather than from the inside out, so he can see the clouds and weather covering the globe. If he could know the paths of the winds, the distribution of temperature from the equator to the poles, could literally see the clouds as they form, the increased accuracy of his analysis, his forecasts could take on extremely significant meaning for all mankind. Everybody talks about the weather, but nobody is doing anything about it. Now somebody is doing something. A start was made on the meteorological satellite program in September of 1958, when RCA showed that a satellite they had been developing for a different use could easily be modified to serve this function. In April of 1959, the TIROS project came under the overall direction of NASA as one of the first civilian satellite projects. TIROS, meaning Television and Infrared Observation Satellite, is more than just a dream. This experimental weather satellite means that man's vision is no longer limited to looking up at the clouds gathering above him. Once the configuration of the electronic equipment was determined, 5 TIROS payloads were built, 2 for test purposes and 3 for actual flight. As development progressed, extensive tests were performed on the components as well as the entire satellite system. TIROS is one of the largest scientific satellite payloads launched to date in the free world. It weighs about 270 pounds. The TIROS satellite is stabilized in space by a spinning motion similar to a gyroscope. It is known that certain materials in a spinning satellite will cause drag due to the effect of the Earth's magnetic field. As the satellite has to maintain a certain spin rate, a test to determine the effect of magnetic drag was made, so proper measures could be taken to restore the spin rate of the satellite. Energy from the sun is converted to electricity by 9,200 solar cells on the satellite. By using rechargeable storage batteries, power is supplied to the satellite even when it is in the Earth's shadow. A high-performance test facility was designed to simulate a vacuum and temperature environment similar to that in which the satellite would operate. A mechanical shaker system subjected component parts as well as the entire satellite assembly to mechanical vibrations 2 to 3 times more severe than it experienced during actual launch. The shock tester is a device capable of imparting severe but controlled mechanical shocks to the equipment. A test to balance the payload was performed on this machine so that the satellite would spin true. The rockets which will be used to restore the spin rate of the satellite were tested. The precession damper test was utilized to prove out the ability of movable weights on curved tracks to dissipate any satellite wobble energy. The eyes of the satellite are 2 television cameras, one with a wide angle and one with a narrow angle lens. A series of individual pictures can be transmitted directly to TIROS ground stations, or the pictures can be stored on 2 videotape recorders in the satellite. The TV transmitter, command receivers, and other control devices are other major units in the satellite which allow 2-way communication between the satellite and the ground stations. The radio beacons provide signals to the satellite tracking stations and double as telemetry transmitters to report on conditions in the satellite. Now, just what is TIROS? What is it expected to do? The satellite's mission did not begin until it was put into orbit. This was the job of the Air Force Thor-Able rocket at the Cape Canaveral Launching Complex. The TIROS payload was mounted on top of the Able third stage rocket. Few seconds in man's age-long search for knowledge can compare in sheer drama with the electrifying moments between countdown and successful orbit. The third stage of the Thor-Able rocket carried TIROS into its first orbital path. On separation, it was then spinning at about 120 revolutions per minute. But the rapid spinning of the satellite had to be reduced before the cameras could successfully take stop-motion pictures. To do this, two cables were wrapped around the outside of the satellite shell. Each ran all the way around with weights attached to the ends. Automatically, these weights were released. This action caused the satellite to de-spin to 12 revolutions per minute within 1/2 second. The precession damper device will correct any wobble that may occur in the satellite's rotation. The Earth's magnetic field exerts a drag on the satellite, gradually reducing the spin rate. In about 30 days, the spin rate slows down to around 9 revolutions per minute. Upon command from the ground stations, pairs of diametrically opposite thumb-sized solid propellant rocket motors are fired. The rockets spin the satellite back up to 12 revolutions per minute. During the 100 minutes that the satellite completes one orbit, the Earth rotates about 23 degrees. The orbit path is from about 50 degrees north latitude to about 50 degrees south. This means that the satellite travels as far north as the Great Lakes and as far south as Australia. But the cameras are programmed to turn on only when they are pointed toward a sun-illuminated area of the northern hemisphere. At 400 miles out, the wide-angle lens will photograph an area of about 700 miles square, with pictures taken every 2 seconds. An overlapping panorama of all the cloud formations for a stretch of about 3,500 miles is received each time the cameras are turned on. By recording the position of the sun as each picture is taken, the satellite also returns information that permits the north direction on the picture to be determined. One of the two cameras takes more detailed cloud pictures that assist the meteorologist in his analysis. As both TV cameras are taking many pictures every 24 hours, a great avalanche of information sent to the ground stations presents complex processing and interpretation problems. A primary ground station at Fort Monmouth, New Jersey, is backed up by stations at Princeton, New Jersey, and Cape Canaveral. Another primary ground station is at Kaina Point, Hawaii, on the island of Oahu. The National Aeronautic and Space Administration's Minitrack system, which runs like a fence through North and South America, provides tracking information that traces the satellite's orbit around the Earth. The information is continually relayed to the National Aeronautics and Space Administration Computation Center at Washington, D.C. The Computation Center can plot the exact path of TIROS and quickly relay the programming information to the ground stations. The programming equipment at the primary ground station sets up the time schedules for picture taking, picture recording, and transmission of the pictures to the ground. At the Fort Monmouth and Hawaii receiving stations, a record on both film and tape is made of all the data that TIROS gathers during its sweeps around the Earth. The pictorial and telemetered information can also be picked up and recorded at the backup ground station at RCA, Princeton, New Jersey. Each primary ground station is capable of tracking, programming, and then receiving pictures and other data from the satellite. They then send all this information to the NASA Computing Center and the U.S. Weather Bureau, where interpretation of all material takes place. An ingenious device which will utilize enhancement techniques has been developed. Still pictures of cloud formations viewed on a television screen can be subjected to various changes by electronic techniques to enhance and highlight essential information which is normally obscured. Light or dark areas in the picture can be examined by increasing the contrast in any portion of the picture grayscale. Outlining is another technique by which areas exceeding a selected light level can be outlined to facilitate study of the cloud density. Background in the cloud pictures can be removed, leaving only the outlines of selected light levels. Differentiation gives a feeling of depth. The edges stand out and the overall configuration can be studied. And now, what comes next in space meteorology? The TIROS 2 satellite program includes subsystems to measure Earth and atmosphere radiation. The measurements indicate where excesses and deficits of energy are being accumulated on Earth. Energy available to sustain the motions of our atmosphere comes from the sun. By measuring accurately the distribution of the energy going into and radiating from the Earth's atmosphere, the meteorologist's understanding of the mechanism of the general circulation of the atmosphere will be appreciably improved. The advanced meteorological satellites could give daily global coverage, even cloud pictures at night. These satellites will have their cameras constantly focused on the globe. A complete pictorial record of our changing weather will be revealed by polar orbiting satellites as their paths pass over the Earth and the Earth rotates within the orbit. Meteorological data presently is hand-plotted on maps prior to analysis, a tedious and time-consuming process. In addition, only limited information is available from remote ocean areas. Certainly, a deeper understanding of the forces of nature will produce tremendous benefits for mankind. Yes, someone is doing something about the weather. This knowledge, we hope, will enable man to prepare for catastrophic storms, blizzards, droughts, and floods, and possibly to achieve some measure of control over the weather. With an outside-in look at our whole Earth's cloud cover, we may be able to take a gigantic step forward in meteorology. The economic benefits could possibly exceed the tragic losses of warfare since the beginning of time. The door to space is open. The mind of man can expand in areas of knowledge as vast as space itself. With meteorological satellites, the realization is near, the rewards unlimited. TIROS is in orbit.